So hi everyone, I welcome you all to the second lecture of the series on which I will be going to discuss mechanical properties of solid. So yesterday we have discussed, I have introduced the what is elasticity, how in general in practical solids are and how it is different from the rigid bodies. And I have also introduced the concept of NCRT, that is that deformation depends on the intermolecular forces, and intermolecular forces have both repulsion as well as attraction. So that is something important. Then I introduced the concept of stress and strain and the types of that. Then I have uh, covered some questions and on the continuation of that, today's lecture I will be starting with two more questions that came into the JEE exam. So the first question is there is a pendulum with a bob. So the a pendulum with a bob hanging with a wire of length hanging with the wire of cross-sectional area and time period t. Now fi find out the change in time period of a pendulum if another bob of mass m is added to the previous one. Options are Tm. Tm is the new time period. Here, Tm is new time period. Tm by T square minus 1 A by mg 1 minus Tm by T square A by mg Tm by T square minus 1 into mg by A, then D is 1 minus Tm by T square mg by A. So I will give 1 or 2 minutes and will give the solution to this question. If you don't know what is the time period of a pendulum, so time period for your hint is 2 pi under root L by G. So that's the original time period. That is not given in the question, but I am giving you as a hint. Okay. So it came in JE 2015. Sorry, the question is find out 1 by gamma. So we need to find out 1 by gamma if another bow mass m is added to the previous one. So gamma is the Young's modulus. Young's modulus of the wire. So these are options for gamma, not the time period. New time period is given Tm. Okay, so let's discuss the solution. So the question is, initially we have this bob whose time period is T is equals to 2 pi under root L by G. Let me use another. So T is 2 pi under root L by G. So this is the time period. Cross-sectional area of the wire is A. Now what happen is, this is initial condition. Now a bob of mass m is added to that. What will happen is So this is the previous pendulum. Then another bob is added to this. That is of mass m. So new time period is Tm. Cross-sectional area will remain same. So we need to first we will be going to find out Tm and then we'll relate gamma. So we know that gamma is nothing but stress upon strain. So that is force net area into delta L by L. And delta L is what? Delta L is the extension that has happened in the string. So delta L here is the extension in the string due to addition of a mass or extra bomb. Okay. So delta L, so force that extra force is nothing but mg. So delta L is mgl by a gamma and new time period is 2 pi under root of L plus delta L by g. Okay, so all time period is t is equals to 2 pi under root L by g. So can we divide these two and see? Because in the options we have Tm by T. So we should divide Tm with Tp. So what we get is under root of L plus delta L divided by L. That comes out to be 1 plus delta L by L. Can we find delta L by delta L from here? So square both sides is equals to 1 plus delta L by L. And delta L by L comes out to be Tm by T square minus 1. Okay. So from here, delta L by L is nothing but mg by a gamma. So equate both. Tm by T square minus 1 is equals to mg by a gamma. We need to find what is 1 by gamma. So 1 by gamma is a by mg. Tm by T square minus 1. Okay, so we need to find 1 by gamma. So 1 by gamma. So the correct option is a by mg. So a by mg and Tm by T square minus 1. So that is the correct option. Okay. So another question is, I guess that comes in JEE Advanced. That is a tricky question. So there is one rod that is a thicker rod. So that is a thick rod. And another rod is welded to this. That is thin rod. So another thin rod is welded to this. The length of the thick rod is 2L. The length of thin rod is L. Okay. Here force F is applied. At this end, it is 2F applied. Both are copper. Radius is 2R. It's R. So the question is, a copper rod is welded by another thin copper rod as shown in figure by a force as shown in figure and is stretched by a force 2F and F respectively acting in opposite direction. We need to find out the ratio of the ratio of elongation in thin wire to that in thick wire. Options are 0.5, 0.25, 4, 2. It's a tricky question. Take 2 minutes to solve this and we'll see. A very tricky question. Okay, so let's find out the solution. So now to solve this question, first we need to understand that the forces that is contributed to the stress on this system. So is it to the forces that are contributed to the generation of stress in the system? Is it F? Is it 2F? Is it 3F? Or what? But so the correct answer lies in finding the force that is creating the stress in the system. So according to me, or the correct concept is that the stress acting on this, either on this side or on this side, is only F. Because we need to find out the restoring force. So the restoring force is 2F in this direction and F is in this direction. So the net restoring force acting on the system is F. So that is the net restoring force. Okay. Now the question is why not 2F? Why not 2F? Because that so F is applied in this direction, 2F is applied in this direction. So the F is so that extra F is going to move this rod in another direction. It is not for the generation of stress. It is for the motion of the system. So let's say if you have a system like this, and if it is like say 16F and it is 10F applied on this direction. So the net force that is creating stress is 10F only. That extra 6F is going to move this rod in the direction of the force. So now restoring force is F for both the thick as well as thin wire. Okay. So now as we know that what is the force and we know gamma is nothing but F by A, L by delta L. So we know that force is this and we want to find out the ratio of elongation. So delta L thin to delta L thick. Okay, we need to find out this. So force for both this wire is same. Force is same for both the wire. Gamma is same because both the wire is made of copper. Length is different and the area is different. And we need to find out delta L. Okay. So delta L is now proportional to L by A. So delta L thin by delta L thick is nothing but L thin by A thin into A thick by L thick. So L thin is L thick is 2L. Area of thick wire is pi into 2R. 4R square. Area of thin wire is pi R square. So this will go, this will go, L will go. So it comes out to be 2. So the correct option is 2. But the where this trick is, or why I'm saying this question is tricky, because or the mistake, if anyone has to be done in this part for finding out the force. People may think that this wire has having a force F and this wire has having a force 2F, but not. It is not the case. The case is this, that complete system has one force that is creating the stress, and that is F. That's why this is the trickiest question. Okay, so all these questions are about the Young's modulus of elasticity and all. So now let's start another concept, or it's related to the yesterday's concept only. So I have introduced uh, you with the stress strain diagram. So let's discuss that stress strain diagram in detail. Okay. First we will be discussing stress strain diagram, all the limits on there on that can be represented from a stress strain diagram, and then we'll have a look on one question related to that. Okay. So I'm plotting that. So stress strain diagram looks like this. Something like this. Let's say this is the O region, and I'm going to divide this region as A, B, C, D, and E. Okay. So if you see from O to A, the stress is directly proportional to strain. So that lies in the elastic limit. But it is not necessary that in the elastic limit, stress is always proportional to strain. Elastic limit does not means to say that stress is directly proportional to strain. So what elastic limit exactly is? In yesterday's class also, I forgot to mention that elastic limit is just not the stress is directly proportional to strain. It is something much more than that. So what elastic limit is actually? So elastic limit is the upper limit of deforming force up to which, if deforming force is removed, the body regains its original form completely. And beyond which, if deforming forces is increased, the body loses its property of elasticity and gets permanently deformed. So the elastic limit is the upper limit. So let's say if you have a rubber, for example, or a spring. So you are stretching it with some force. So it is, so when we applied a force on this, then it gets stretched. So when it's get stretched, then stress may or may not be proportional to strain, but in elastic limit, it will get back to its original position. So the question is the elastic limit lies till OA only? No, that is not the case. Elastic limit lies from OB and OB. So OB is divided into two regions, that is OA and AB. So in case of OA, stress is directly proportional to strain, and in case of AB, stress is not proportional to strain. Okay, so that is the elastic limit. Hooks give this according to Hooke's law also. By some experiments, he showed that stress is directly proportional to strain, and when stress is directly proportional to strain, then he introduced the concept of proportionality for the case of spring. See, so in generally, Hooke's law is that F is equals to Kx. So K is the proportionality constant given by the Hooke's law. So whatever the force used to increase the stress in the system and whatever the deformation is directly proportional in the elastic limit, and that is given by K. K is generally called as spring constant. So now this is all about the limit from OA and AB. Now what is happening after B? Let's think about it. So when we go from B to C, so even for a small increase in stress, strain is very large. And this type of behavior is observed around point C, and at this stage, wire begins to flow like a viscous fluid. That is, don't worry too much about this point because you may not know about the properties of the fluids at this moment, but when we discuss about it, I will tell what is it. But in general, point C is called to be a yield point. And when we are going from B to C, the stress is not proportional to strain, as well as it is it loses the elastic limit. The body on which the stress is generated loses its elastic limit after point B. And C is called to be a yield point. Why C is called to be a yield point? Because from C to D, any material shows a plastic behavior. So from C to D, it is showing a plastic behavior, and B to D is called to be as plastic region. The point D, when we reached point D, so that is the maximum stress that any body can bear. After that, it will get big. So once it reached the maximum stress, that's the maximum stress that is generated in any body. So D is the point of maximum stress and called to be as breaking point. And then E is nothing but a rupture point. So based on these properties, so just want to remind you. So O is in OA, it is the elastic limit where stress is directly proportional to strain. AB is also elastic limit, but stress is not directly proportional to strain. B to D is a plastic behavior. B to C materials flow like a fluid. But B to D has showing a complete plastic behavior, and it loses the elastic limit once it goes beyond point B. From D to E, so D, anytime any further stress from above D will leads to a rupture. So that is the stress strain diagram. So that is the stress strain diagram, and then we will going to discuss. So from this stress strain diagram, we are able to predict that whether the material is ductile, brittle, or is it elastomer. Now, if I'm saying the material is ductile, so ductile material or the tensile material. So these are those materials which has large plastic region. Large plastic regions means to say that which has higher BD. So for any material, if BD is high, then we can can call it as ductile or tensile material. So that is all about the ductile and tensile material. In general, we use a universal testing machine. I'm just telling you about in general to predict the material by applying a stress, and we plot this diagram, and from that diagram we will be able to tell whether the material is ductile or a brittle. So brittle material are those which has a small plastic region, and elastomer are those when there is no plastic region, only have elastic region. So material of elastomer is rubber. Brittle is, you can say, glass, and ductile are generally metals. So these all about the properties. So let's take one question on this that came in exam as a multiple choice question. So the question is, the plot is given for two materials, that is P and Q. Strain versus stress. So it is something like that, that is P and that is Q. Options are gamma, Young's modulus of P is more than that of Q. P is more brittle. P is more ductile. Another question is P has more tensile strength. So let's think about this question a bit. I am telling this is point A, this is point B, and just relate this with this diagram and answer this question. So it has multiple choice. So maybe more than one options are correct in this question. So let's see. So gamma is nothing but gamma is stress upon strain. So from this, the slope of P and Q is strain upon stress, and that is gamma. So that is 1 by gamma. So from here we will be going to get what is 1 by gamma. So that is 1 by gamma. So from here, from the figure, 1 by gamma of P is greater than 1 by gamma of Q. So gamma of Q is greater than gamma of P. The first option is not correct. Then second option is P is more brittle. So we have, so which has a small plastic region that is brittle. So it has some amount of plastic region. So because it has a plastic region and Q, so P we can say is more ductile, not a brittle. So P is more ductile. So it is all compared. P is more brittle than Q. So P is more ductile obviously than Q because it has this region. It has plastic region. Then Q, if you see Q, then it doesn't have a it has a very small plastic region. So Q is actually a brittle material. So the last question is P has more tensile strength. Yes, P has more tensile strength because if you see it has a plastic region as well as it is uh, it is going beyond this point, beyond B also. So it has more tensile strength. So the correct option are C and D. So this is all about the stress strain curve. So in tomorrow's lecture, I will be going to cover the potential energy stored in the deformed spring or energy stored in stressed wire. So I will be going to discuss this in tomorrow's class and I will be going to discuss the formula of this. So I will be writing now the formula and we will be going to derive this in tomorrow's class. So why the concept of energy in a stored wire came into picture is because when we deform something, so there is some amount of potential energy stored into that. So we need to find out that potential energy per unit volume. And that potential energy per unit volume is equals to half into stress into strain. That's the formula. So that all comes from the first law of thermodynamics that states that energy can't be created nor be destroyed, but only convert from one form to another. So energy. So what is happening in this case is when you stretch, let's say you have a spring and you stretched it a bit. So the work done in stretching this spring, so work done is converted into the potential energy of the stretched spring. Similarly, if you see in general what we called in English, I don't know. It's a Goel. So you have this kind of structure. So that's a rubber band. So that's the rubber band. That is the rubber band. So if you put a stone here and you stretch it back, so while stretching it back, this is the potential energy stored in a rubber. This is the potential energy stored in a rubber, and then when you push, when you lose it, so this potential energy, when you remove your hand from here, this potential energy converted into this will give wind to the stone, and this stone now has a kinetic energy, and that will go. So this potential energy is stored in a rubber converted into the kinetic energy of a stone, due to which it has some velocity and have some projectile motion in general. So all these concepts I will be going to discuss in next class, that is tomorrow. So tomorrow I will be going to discuss the energy stored in the stretched wire, and then I will discuss some of the questions related to the mechanical properties of material. Some more questions that came in various examinations, and then we will following that we will be having properties of fluids and then thermal properties of material. So okay, so let's end this discussion. Thank you.